Hello, my name is Christian Neumayer, and I'm the first author of the paper General Sum Multi-Agent Continuous Inverse Optimal Control. My co-authors are Oliehoek and Gavrila. We are all with the Technical University of Delft, and I'm also with Mercedes-Benz. Now, we are interested in solving autonomous vehicles, and in particular modeling the behavior of other traffic participants. These could be other human drivers or pedestrians or cyclists. We are describing this behavior in terms of Markov Decision Processes. So each agent has a so-called state. An agent could be a cyclist, a pedestrian, or another driver. And the state could be a position, a velocity, or anything else. Then each agent can also take an action to go from one state to another state, to make a transition through time. This could be a simple throttle, like acceleration, deceleration in a car. This could be a simple translation in position, like a pedestrian moving to the left or right. In this framework, it's important to know the so-called reward function that describes what an agent is going to do and how it's going to interact with other agents. So it could be a reward for going to a certain position. It could be a reward for not colliding with a car, for example. Now, engineers may hand engineer these reward features to get an approximation of real-world behavior, but there are always parameters that we don't really know and that we have to fit using real-world data. Also, we may use nonlinear reward approximators like neural networks, which are even more complex and have more parameters. Question is how to do that. And here inverse reinforcement learning comes in. And we're going to address inverse reinforcement learning in the multi-agent setting without doing the reinforcement learning part, which usually is the hard part and which is not necessarily stable and it's complex. So we're getting rid of that. So some notation first. The state here is X. K is the index that tells us which agent we're talking about. U is the action. X without an index means all the states of all the agents. So it could be positions, velocities of each agent. And the actions, U is the collection of all the actions of all the agents. All right, we're going to model the agents suboptimally. So a human may not do the same thing exactly the same. So driving along a street, it may steer slightly differently, may accelerate, decelerate slightly differently. So humans are not optimal in the sense that they choose the best action, but a set of actions which are equally good or almost as good. So we're using a maximum entropy framework where the agent maximizes the reward and the entropy of the policy, so it maximizes its choices at the same time. Here the Bellman equation is slightly different to the standard Bellman equation. Instead of a max operator here, we have a soft maximization, so this logarithm integration and this exponential. But other than that, it's similar to the standard Bellman equation. And we're in the multi-agent case, and the action value function needs to consider what the other agents are going to do. And this is a stochastic policy for each agent, so we have to integrate over the actions of the other agents. Other than that, it is the standard Bellman equation, except for the stochasticity and the soft maximization. Okay. Now, we're going to look at this one step at a time. So an agent moves from one state to another. And now what we have to do is to get rid of the reinforcement learning. In inverse reinforcement learning, we do an approximation. And we do this for this one transition from X to X prime. And first approximation we do is we linearize the dynamics. The dynamics may be highly nonlinear. Okay, they could be anything. And we do this simple approximation where we end up with these AX plus BU. And this is not a global approximation. It is specific to this transition from that state to that state that you observe in the data set. The transition from here to there is a different approximation. Again, also an A and B matrix, but these are different. Okay, so it's not global, it's a local approximation. Next approximation, we approximate the reward function with a second order Taylor expansion. So it's quadratic in the states and actions. You may have seen this before. There is a paper, we're also going to cite this later on, called Continuous Inverse Optimal Control, who did a similar algorithm for single agent case, not the multi-agent case we treat, but it's quite similar. Okay, and now that we have these two approximations, what we can now do is we can actually derive the policy without doing the reinforcement learning. So just taking the data that you observe, a trajectory of a car driving around and interacting with another car, we can now derive, starting from the last time step of this finite horizon problem, and going backwards, we can now derive the value functions and the policies that correspond to these value functions. So this is somewhat similar to the linear quadratic games, which are discussed in the work that I cite here. And in that case, we also have linear dynamics and quadratic rewards, but they use a standard Bellman equation and they cannot easily infer the reward function that explains the behavior of the multi-agent in the multi-agent setting. But using a max-end framework, we will be able to do so, interestingly. So now we start moving. So for the last time step, we now calculate the action value function, which is simply the reward function, which we approximate using a second order Taylor expansion. So that's just quadratic in the states and actions. And we have the policy of the other agents. Now, we do the same approximation with the other agents of the reward function and the dynamics. So what we end up with is a Gaussian policy also for the other agents. So all the agents have a Gaussian policy. And a Gaussian, so some exponential minus y square here, and then some second order polynomial, we can solve this analytically, okay? So we can just do it on a piece of paper. We don't have to do reinforcement learning to solve this for this step, what the policy is and the Q function. So we just do that. And then in the next step, we need the value function. And we have the soft maximization operator. The Q function now is also quadratic in the states and actions. And so we can also solve this integration. And the value function is also going to be quadratic in the states. Again, so when we move to the next step, we do the whole thing again. Just in this case, there is this value function, not just the reward function, but that is quadratic, that is quadratic. That turns out to be Gaussian. We can solve this. So we do this for each step until we're at the end. So what we can now derive naturally is the policy. And given the policy, we can now maximize the log likelihood. So let's assume the reward function has parameters that we don't know. It may be that the reward function is a neural network. It could also be something that we hand engineered and has just a couple of parameters. Now what we do is we sum up the log likelihoods for these agents and we maximize this parameter with a simple gradient step, for example. So the algorithm looks as follows. We derive, given a reward function, an initial reward function with initial parameters, we derive the Q values, the value action values for the whole trajectory, thereby knowing the policy. And then we maximize the log likelihood of the data doing a gradient ascent step. Now we get new reward parameters. We do the same thing again. We move through the whole trajectory, all the agents, and then maximize the log likelihood again. So this goes on and on and on until convergence. And that's how we derive the reward parameters for multi-agent interactions. Now, let's show this in a simple experiment. So we have two toy experiments to demonstrate the benefits of this algorithm. The first one is an experiment where the right agent is attracted to the left agent, so it really wants to move to the other agent. The other agent, on the other hand, gets a reward when this agent is at this goal position. All right. So what the left agent ends up doing is it's pulling the right agent to the goal position. So the initial condition could also look different. It may be over here, the left agent, the right agent over here. So the left agent has to move all the way to the left to pull this agent over there. But the point is that the left agent needs to understand that, okay, it needs to move and it can actually influence the right agent. So let's look at this. So first of all, we just look at quadratic rewards. So these A1, B1, and so on, these are reward parameters that describe this scenario. Okay, we perform value iteration. It's a one-dimensional problem, so we can just use value iteration, where we discretize states and actions to derive the ground truth data. We have a ground truth reward function, and we create ground truth data, and then we feed that to our algorithm, general sum, continuous inverse optimal control. And we also feed it to continuous inverse optimal control, which is a single agent algorithm. Now you may wonder, why even use that as a baseline? Well, because a couple of papers already use this to describe interactions, and it is reasonable thing to do. A lot of interactions in traffic scenarios are rather simple. For example, I go 50 kilometers an hour along a street with a car, and 10 meters in front of me there's a pedestrian walking to a curbside. The pedestrian is aware of me. What is going to happen? Well, it's not very complicated. The pedestrian is just going to stop, right? So there's a collision reward. The pedestrian doesn't want to get hit, but it's not a complex interaction. So for this type of scenario, you can absolutely use these single agent inverse reinforcement learning algorithms. Now, but this scenario here is a scenario where the behavior of the agent that moves around to pull the other agent towards the goal position, it's not enough. You really need to understand that it can actually influence the other agent. And what we can show here is that we get close to the ground truth reward and the log likelihood of the ground truth data, whereas the single agent inverse reinforcement learning algorithm fails to understand what is going on. We can also do this for a Gaussian interaction reward. So for the quadratic reward, our algorithm is exact. Basically, for the Gaussian one, it is not. It's an approximation only. And here also it demonstrates a reasonable performance and gets close to the actual reward parameters. Again, the single agent version doesn't understand what's going on, doesn't understand how to model this. We also did this with a repulsion experiment where now this agent pushes the left agent towards the goal position, and just a visualization. So this indicates the position on this line and indicates where the right agent is moving on this line. Gray is the ground truth data. Blue is our algorithm, general sum continuous inverse optimal control, so the behavior that it reproduces. And continuous inverse optimal control just doesn't understand what is going on. Okay, so it's not sufficient to use this algorithm for these types of scenarios. So to sum up, our algorithm can infer the reward for multi-agent scenarios where each agent has a different reward function. We use local approximations of the dynamics and the reward function to achieve this, and thereby do not need to perform reinforcement learning, but we can actually propagate the gradient directly into the reward function. Thank you for listening, and I'm looking forward for your questions.